Okay, so today we're going to talk about molecular geometry. You've already learned how to write a good Lewis structure. You've already learned how to calculate um, formal charge to determine if it's a good Lewis structure. And today what we're going to do is take those Lewis structures and draw a molecular shape or know what the molecular shape should be. Okay, and we use a tool that you've learned in honors called VSEPR, valence shell electron pair repulsion theory. And the theory is based on the fact that the electrons repel each other. Okay, so they want to be as far away as possible. Okay, it's important to note that if you have a lone pair on an atom, it has a greater repulsion than any of the bonding pairs. Okay, so that's important to know. So those lone pairs want to get farther away than any of the bonding pairs. Because of this, you can predict shapes and bond angles from the repulsion. Okay? And the way to do it is you look at the center atom, only the center atom, and count all the electron domains, and we'll go into what that is. If there's no center atom, the structure must be linear. Okay, so basically if you have two atoms, it's always linear, no matter what. Okay, now I want to go into two before I go into this VSEPR, just to review. What is an electron group? Remember when you look at the formula or the drawing, you're counting electron groups from the center atom. Okay, so if you have, say, CH4, okay, remember you're counting one bond is one electron group. Okay, so these are what the electron groups are. A double bond is also an electron group, is one electron group. Okay, so a single bond is an electron group, a double bond is an electron group, a lone pair is one electron group. A triple bond is one electron group. Okay, so this has 4 electron groups around it. 1, 2, 3, 4. Okay, nitrogen has 1 electron group, even though it's a single bond. So that's how you count it. So remember that 1 electron group is a single bond, 1 electron group is a double bond, 1 electron group is a lone pair, and 1 electron group could be a triple bond as well. Okay, now this is our VSEPR sheet. It's going to be in your reference materials on page 1. Okay, this is what we used in honors, okay, to predict the shapes of molecules. Okay. I tell the kids that you need to look at how many bonds you have and how many lone pairs you have. And that's going to tell you the molecular shape. Okay. You're going to need to know the molecular shape, the bond angle, the polarity, the hybridization of all of them. Okay. However, okay, I'm going to teach you how you don't have to memorize hybridization. You don't have to memorize polarity. Okay, and some of the shapes based on the repulsion are very obvious what they're going to become. Okay, but in this case, you do have to know, a lot of these shapes. Okay, so this is your VSEPR sheet to look at. So you're counting the bonds, the bond groups, the lone pair groups to get your shape and your bond angle. Now, I'm not going to go through all of them. Okay, so hybridization, what is that? What is that? Okay, it's a formation of newly shaped orbitals on the valence electron. So what happens is it takes these unhybridized orbitals and basically takes them to a medium energy level, puts them all at the same energy level so that they can bond with other orbitals. Okay, so remember what we know about atomic orbitals. Okay, we have the S, the P, the D, and the F. And what happens is when they start to form bonds, they create this bond, they create this hybrid. Okay, either raising the energy level, lowering the energy level so that they can bond together. Okay, so just for example, the tetrahedral family. Remember what a tetrahedral is. A good example of a tetrahedral molecule would be methane or carbon tetrahydride, right? If you drew carbon, okay, and looked at it, you would see you have on the center atom, and all you're doing is looking at the center atom, you have 4 bond groups, no lone pairs. That's a tetrahedral shaped molecule. Okay, it also has bond angles of 90 degrees between. Yes. Okay, so when it makes this molecule, the 4 orbitals, okay, on the carbon alone, just the carbon, have to change shape and energy in order to accept the hydrogen. Okay, so what I'm going to draw is the valence electrons for carbon. Again, this can be a little confusing, so if you don't understand it, it's okay. But what happens is if you draw the valence electrons for just the carbon, you know that carbon has 4 valence electrons. Okay, so it's got 2 in the S, because if you're just drawing it, let me just draw the whole configuration. 1s2, 2s2, 2p4. Remembering that the only ones that are in the valence are these. I'm sorry, it's 2p2. Okay, so it's got 4 valence electrons. So these are the ones that are going to hybridize. They're the ones that are going to be bonding with the hydrogen in this case, okay, in this example. Okay, so what happens is you drew the orbital diagram, and you would have a full S sublevel, and then you would have 2 electrons in the P. Okay, what ends up happening is it hybridizes to become this. You can see the lower energy, the higher energy. It hybridizes to become this sp3 hybrid, making openings for the hydrogens to come in here and bond in all 4 spots. Okay, so that's technically what's happening. Okay, and we call that an sp3 hybridization. And I'm going to show you a quick way to calculate or to understand or remember hybridization. Because there's an S and P and 3. So S has 1, P has 3. Yeah, you'll see. Okay, so this is really just showing you a picture of, these are the regular, okay, the top row here. Again, this is still sp3. This is still like the methane thing we're talking about. The top row is just your normal orbitals before hybridization. And then the bottom row is showing you the sp3 hybridized orbitals. Okay, so these down here are the sp3. Up top are your regular sp, x, py, pz. And this is where like your hydrogen is going to come in, which is just an S, and start bonding on each. Okay. Now, I'm just going to read this off, but I'm going to show you. You may say, "Oh, how do you know trigonal planar has an sp2 hybridization?" I'm going to show you how to figure it out. It's got 3 electron domains, a trigonal planar. Okay, remember ammonia. Oh, not ammonia. Excuse me. I'm thinking trigonal pyramidal. BF3 is trigonal pyramidal planar. Okay, it's got 3 bond groups, no lone pairs. That's trigonal planar. Okay, 120 degrees between each. sp2 hybridization. Okay, all you're doing is you're counting the number on the boron. Okay, a lot of times trigonal planar has a double bond. Okay, this is an sp2 hybridization. Okay, you have a 1s, 3p, and then they make 3 sp2. Okay, a linear family has what's called an sp hybridization, often has a double or triple bond and obeys the octet rule. Okay, you know, nitrogen has the triple bond. Carbon monoxide, I believe, has the double bond. Okay, and there's sp orbitals. Okay, 1s, 3p, 2sp orbitals. Okay, and that's where the bonding is going to go on. Okay, now here's my little cliff notes. You're welcome. Okay, for this, how to determine hybridization quickly. It's very similar to how you determine the molecular shape. You count the regions of electron groups. Okay, remember, a group is any of those electrons that are close to the center atom. Okay, so just like when we do shapes, an electron group is a single bond, a double bond, a triple bond, or a lone pair, right? So if you're looking at ammonia, which is a trigonal pyramidal, okay, and you're counting these groups, these electron groups, you're only looking right here, you have, if you're looking for the shape, you have 3 bond groups and 1 lone pair, okay, which when you looked at your VSEPR sheet, you would see that that is trigonal pyramidal. For this, you're looking at 3 bond groups, 1 lone pair, that's 4 total electron groups, right? Which would be sp3. Okay, and you can think of it as S counts as 1, P counts as 3, 1 plus 3 is 4. Okay, if it's something like 2, it would just be sp. Okay, if you had that boron, let's see, CF3. Okay. Here you have 3 bond groups, no lone pairs. That's going to be a trigonal planar. Okay, 3 bond groups. Okay, that would be S, which is 1, and then you need 2 more, P2. So it's sp2 for trigonal planar. Okay. Now there's 2 types of bonding that happens. Okay, when these orbitals get hybridized. 2 types. One's called a sigma bond, one's called a pi bond. Sigma and pi. Okay. Single bonds are classified as sigma bonds. So single bonds are always sigma bonds. Okay. It's basically an overlapping. So if you have a hybridized orbital, I'm going to show you a picture. Actually, I'm going to show you a picture right here. Here is a carbon bond. Actually, this is going to be ethene, okay, which is a triple bond. Okay, so this is ethene. This right here, the overlapping, the direct overlapping is called a sigma bond. The indirect overlapping right here, this bond right here is called a pi bond, and there's 2 pi bonds right here. So it's kind of like not a direct physical overlap. And let me go back. Okay, so that's what it looks like. So if we go back and read our slides, okay, the first shared pair of a double or triple bond is called a single bond. Excuse me, sigma bond. Okay, a pi bond involves non-hybridized p orbitals, right? Double bonds have 1 pi and 1 sigma. Triple bond has 2 pi and 1 sigma. Okay, so if you made yourself a little chart, okay, which I have in the past for the kids. We used to actually teach sigma bonds and pi bonds in honors, okay? So a single bond, one bond, has one sigma bond right here and no pi bonds. You have a double bond, it has one sigma bond and one pi bond. And if you have a triple, like showing here with ethene, you have one sigma bond and two pi bonds. Okay, so that's what's happening. Okay, so we're going to see if we can practice these. Let me go through a couple more things. Actually, I think I'm going to hold off on the practice for a minute, just to kind of finish up the lesson. And then we'll go back to practice, I think, at the end. Okay, so I want to talk about, okay, so we talked about VSEPR. If you're still not sure how to get the molecular shape, you may need to go review some of the honors videos. Okay, but let's talk about a dipole again. We've talked about covalent bonds being either polar or nonpolar, okay, just the bond itself. And remembering it's not an even sharing if it's polar. Okay, but even if you have polar bonds in a molecule, now we're talking a molecule, even though the bonds are polar, you can have these dipole moments cancel each other out and make a nonpolar molecule. It's kind of like in physics, equal and opposite forces cancel each other out. It's the same thing with these dipole moments. They can cancel each other out and make a nonpolar molecule. However, if there's a net dipole moment or a net force, then it's considered a polar molecule. Okay, so let's talk a little more about polarity. Okay, if it's going to cancel out, this is for a nonpolar. Okay, the individual dipoles, and when I say nonpolar, I'm talking nonpolar molecule. Okay, not a bond, a molecule. In order for this to happen, they must be equal in size. Okay, so it's got to be the same external atom, and they have to have a symmetrical shape to cancel the dipole moments. Okay, shapes that can potentially cancel dipoles are linear. Okay, right? You have two of the same molecule, right? They each have a dipole force, but it's canceling each other out. Okay, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These shapes can, as long as they have the same outside elements, can cancel the dipoles out. Okay, remember trigonal planar, like that BF3, they are all evenly, you can draw the dipoles will cancel each other out. Okay, now here's some more examples of drawing dipoles and seeing what's happening. You can see in the first one, I think I drew a dipole in the last one, I probably shouldn't have, but the oxygen, there is no dipole, there is no permanent dipole moment. Okay, carbon monoxide, you can see that there's a dipole towards the carbon. And carbon dioxide, because it's even, there's double bonds, the dipole cancels out. So this dipole cancels out with this dipole. Okay, so to cancel or not to cancel, that is the question. Okay, carbon tetrachloride, definitely tetrahedral cancels each other out, all 4 dipoles. Okay. Something with fluorine on top here obviously is going to have a net dipole towards that fluorine, so it will not cancel out. Okay. All other of the shapes with polar bonds are classified as polar overall. Okay, and just a hint, anytime an oxygen or nitrogen is bonded to a different element, the molecule will be polar. Okay, so if there's ever an oxygen in it or a nitrogen bonded to something other than itself, it'll be polar. Okay, and here's, you can see the electron density, hydrogen chloride. Okay, and you can also see water molecule, the electron density in the oxygen part. Okay, so what we're going to do now is practice polarity. Determine the overall polarity. Remember, your choices are polar or nonpolar. Okay, so I'm going to give you like 10 minutes to do that. I'm just going to keep you in this same groups right now. So if you remember to draw, remember to know the polarity, you have to know the shape of the molecule. Okay, so you guys, give you about 5 minutes to do that. See if you can do that.